Welcome back to our course on probability theory and stochastic processes. We learned about Markov processes. We had the strong Markov property last time, and today the chapter is called the distribution of Markov processes. And for this, please recall the Kolmogorov extension theorem, which tells you that the distribution of a process is determined by its finite dimensional distributions. So let's get started. So, the distribution of a Markov process. As I just said, the finite dimensional distributions play a certain role. And first, we have to see how we come up with them. So, up to now, we learned about the Markov kernels mu st. So, that was the probability to go from some xs to some set b between times s and times t. And transition operators. And we always had the duality that these two carry the same information, so to speak. So the only difference is that the mu's give you probabilities to go somewhere, and the t's give you expectations of some functions. Okay, usually f is something continuous, but if f would be an indicator function of b, let's say, then tst, this indicator function, is equal to the mu st. We also introduced notation mu times nu and mu nu, which was the following, and which we will need in this video extensively. So mu nu was the probability to go from nu, so from x, to some set a using the Markov kernel mu. And then wherever you are in A, let's say that is some point y, to go from y to b according to the kernel nu. That's the formula. So y is in A, z is in b, and I go from x to y and using mu, and from y to z using nu. And the special case where this here, the A, is the whole set, then I call this mu nu. And then, of course, I do not need the first coordinate because it's the whole set anyway. And I'm renaming the second one to A, and I have this. So that's going from X to something using mu, and from the something to go to A using nu. So that's this formula here. And using these, we can define the finite dimensional distributions of a Markov process x. So let's assume the distribution of xt, so the one-dimensional distribution is given by nu t. And I'm having the Markov kernels mu st. Then the finite dimensional distributions, okay, that does not come as a big surprise. So you start in t0, you go from, t0 to t1 using the Markov kernel mu t0 t1. You end there somewhere, and you go further until you go from tn minus 1 to tn. And remember, we are in the Markov case, which means that the past is independent of the future given the present. And for this reason, I can really write it like this. Because, for example, for this times here, the state it's t0 doesn't matter because the Markov process, so you can safely go from the state at t1 to the state at t2 using this Markov kernel. And that is also expressed in the last formula here. So the probability to be somewhere given ft0 is exactly given by this here. And the right-hand side only depends on xt0. That makes sense. Because conditioning on ft0 and on xt0 is the same because we are in the Markov setting. So I'm not showing you the formal proof of this lemma because I just explained you how this formula is to be understood, and then proving it really is just writing this up properly. The video of today is mainly about this these called Chapman-Kolmogorov equations, and they are the following. So this here. Remember, so the notation mu st mu t nu is this product that we had here, mu nu. So here we said I'm going from x to somewhere using mu, and from the somewhere going to a using the kernel u. And when you do this in the Markov setting, so you go between times s to somewhere at time t, and from the somewhere to some set using the Markov kernel mu tu. That is the same as to go from s to u immediately without stopping at t. So this here is an equation which should hold for Markov processes. That's the result. So you have a Markov process with these Markov kernels, then this here holds. And the same is true also for the transition operators. So transition operator from S to T, T to U, applied to F is the same as applying the transition operator from S to U. Sorry. So why is that? How could we prove this? So I'm starting in the first equation here on the right hand side, and I'm writing mu su from xs to some set a. So that's by definition the probability to be in a at time u, conditioning on fs. Well, I can also write that's the probability that the tuple xt xu is in, well, something times a given fs. And this, according to what we had on the last slide, that's mu st times mu tu to go from xs to e times a. Well, and this is just by definition this product mu st mu tu from xs to a. And I'm already done. Yeah, because that was what I wanted to show. For the transition operator, T S U F of xs. What's that? That's by definition the expectation of f of xu given fs. Because of the tau property of the condition expectation, I can write it like this: the expectation of the condition expectation f of xu conditional on ft and conditioning the whole thing here on fs. And since we are in the Markov setting, conditioning on ft and on xt is the same. And this here again can be written using my transition operator ttuf of xt and condition this here on fs. But again, that's just a function here. So that's a function applied to this. And therefore, I can again use the definition of the transition operator tst applied to ttuf and the whole thing here applied to xs. And that's exactly what is claimed here. Okay, so that was one direction. So if we start with the Markov process, then the Chapman-Kolmogorov equations hold. The more interesting question is, if I have a set of Markov kernels or transition operators that satisfy this property here, do we have a corresponding Markov process? And the answer is here. So that's this result here. Okay, I have an index set, I have the initial condition, I have mu STs are a family of Markov kernels, or equivalently TST is a family of transition operators, satisfying the Chapman-Kolmogorov equations, either for the Markov kernels or for the transition operators. Then it is claimed here there is a Markov process with the desired kernels or operators. So it's really, you only have to show that you have Markov kernels which satisfy the Chapman-Kolmogorov equations, and then you get a Markov process. So that's a way of constructing a Markov process. Of course, by our usual duality, TSTF and UST, well, they can be written in the same way, or in a similar way, such that we only have to show what we need here for the first assertion, which means only for the Markov kernels. So we assume you have the Markov kernels with the right things. And using them, we can define a family of finite dimensional distributions, nu T1 until Tn, and so on, where T1 until Tn is a finite subset of I, given by, well, this here. Yes. So that's the definition. And since the Chapman-Kolmogorov equations hold, this family here is projective, because you can just integrate out here these things. Okay. But that's not enough. We have to show that X really is a Markov process. So first of all, that's a projective family, and by this we know by Kolmogorov's extension theorem that there is a corresponding process or distribution of the corresponding process. And for this process, we then have to show now that this is a Markov process. And how do we show that something is a Markov process? Well, we need to see if the property holds, the conditioning on Fs or on Xs is really the same. And how do we do this? We are going to show the following. So we're going to show that if A is in Fs, then the probability, okay, xt, for t bigger or equal than s, of course, the probability that xt is in B, conditioning on Fs, is the expectation of, well, mu st from xs to B over the set A, and I forgot the set A on the left hand side here. So I have to also, xt in B, I have to show this here. I have to show this. And that is valid for all A in Fs, because then by definition this here is the same as the conditional expectation of the conditional property that xt is in B, conditioning on Fs. And this here is the conditional probability that xt is in B, conditioning on Xs, which is of course also Fs measurable. And by the defining property of the conditional expectation, then we have that the conditional expectation of xt in B is independent of the past of, so it's independent of Fs conditioning on Xs, and that's exactly the Markov property. So we need to show this equation here. Well, we take some finite set J out of I. The maximum of J is S, and S is less than or equal to T. And when we have this, we can write that the probability that XR are in J is in A. So that's a set of these where we can evaluate the finite dimensional distributions. And xt is in B. Well, that's so we can evaluate this because we know the finite dimensional distributions of our process X. And this is in this case here nu J union, union and T. So that's what we defined here. So that's connected to what we had here, because here we had a set of time points, and we also have a set of time points here. A times B, where A covers the first coordinates which are in J, and the B covers the coordinate in T. And well, we can write that as the expectation of mu st to go from xs to b, and well, xr r in j is in a. Yes, so we have this. So A was a set here of the Borel sigma algebra of e to the power of j. So A is dealing with elements less than or equal than s. In particular, all these A's here, they form a generator for the sigma algebra Fs. And since we have proved this here, that holds for all A in Fs. And for this reason, when you look at this here, xt in B and A is in Fs, that's exactly a set of this form which we had here. And going from the generator to the full sigma algebra means that we can replace this here by this set A on the left and the right hand side, and that's exactly what we did see. So that's the right hand side, that's the left hand side. And as I said before, by the defining property of the conditional expectation, we have shown the Markov property of our process X. And we are done with this thing here. Okay, last slide for this video. That's just more or less a remark. So if we have a nu and a mu st which satisfies the Chapman-Kolmogorov equation, so apart from this here is theorem 15.17, which I should have mentioned. So if you have the nus and the mu's as written down here, then we find a probability distribution on the path space, which is the distribution of our Markov process X, which we gave here. In addition, so Px is this probability distribution where we start in small x. So that's with a deterministic starting point, but we would like to have a p nu, where nu is some probability measure on our initial condition. Well, and that can be defined as follows. We have all these px's, and we mix them using our measure nu, which is the initial condition, and then we get p nu. So that's really also a property, how these p nus here interact for different nus. So p nu arises by mixing the px's over this initial distribution nu, which is maybe also pretty clear that this must be the case. Okay, great. Next time we will deal with more constructions of Markov processes. In particular, we will not only deal with our Markov transition kernels and transition operators, but also with so-called generators. And these generators, they generate semigroups and operators. Okay, see you then.